So, in this present class, uh, we are discussing about magnetic properties. Actually, after a lot of uh, shrinking, we had a very less amount of syllabus related to magnetic properties. Basically, you need to have some idea about magnetizing field, intensity of magnetization, susceptibility, bus, and classification of magnetic materials. This is what expected uh, presently for the mains part. See, when we are dealing this, I just want to tell you we are speaking about a short bar magnet. When you have a short bar magnet, say for example like this, it's a short bar magnet. You will call this as a south pole and this as a north pole. Effectiveness of the magnetic property more concentrated at the ends, and those regions are what we call as poles. The magnetic moment is literally pole strength times 2L. This is analogous to charge times 2L. The magnetic moment is a vector which is always directed from south pole to north pole. South pole to north pole inside magnet. Inside the magnet. See, you have a magnet like this, and this magnet, if you cut into two halves like this, left half and right half, each part magnetic moment will become half, m by 2, m by 2. If you cut the same magnet like this, in this case also, each part's magnetic moment is m by 2. In the first case, because the length is halved, magnetic moment is halved. In the second case, since the pole strength is halved, magnetic moment is halved. Right. Next. See, if a wire is magnetized, you have a magnetized wire. Say, for example, this is the south pole and this is the north pole. And the length right now is some L. No, what that I have done right now is I have bent into a shape equal to arc. South and north. Theta. No. Will the magnetic moment remain the same? No. Why? The effective distance between the poles is no longer L. It is now a different thing. This is R. This is R. And you already know this distance is going to be 2R sine theta by 2. Agreed, boys and girls? That is 2R sine theta by 2. Right. So now the previous magnetic moment and the present magnetic moment ratio, if I can take, nothing affected to pole strength. What affected is the effective length of the magnet. Previously, no, by the way, one more important point, L is nothing but R theta. Length of the arc is radius times the angle. The m dash by m is now simply 2r sine theta by 2 divided by the length. So literally this is sine theta by 2 by theta by 2. So this is how magnetic moment is affected just because of the bending. For example, when such magnets, so we are taking short bar magnet usually. If we are taking short bar magnet as a combination like this, south pole, north pole, magnet 1, south pole, north pole, magnet 2. This total is equivalent to a single magnet whose magnetic moment is M1 plus M2, like dipole solve. On the other hand, okay, if you are taking the magnets like this, basically I am writing short bar magnet only. This is north pole, this is a south pole, this is a south pole, and this is a north pole. In this case, the equivalent magnetic moment is M1 minus M2. Equivalent magnetic moment is M1 minus M2. Please try to understand the differences between whatever that we are seeing here is a different combinations. I am just displaying M1 minus M2, M1 plus M2 are different combinations, and the arrangement is because of the fact that you took the configurations different. Same thing you can apply for electric dipoles also. Now, if the magnetic dipoles are like this shape, T shape, or L shape, or plus shape. In all these forms, remember they are short bar magnets. The net magnetic moment is under root M1 square plus M2 square. Any doubt? Yeah, no. Pole strength. Pole strength. Ampere. Very good. Magnetic dipole moment, you are writing it like this. This is ampere meter. Ampere meter. Whereas magnetic moment units will be ampere meter square. Okay, na? Ampere meter square. Right. Next. So basic idea. You already know when you are placing such a magnet in a uniform magnetic field like this. This is a region of uniform magnetic field. When you place a bar magnet, the torque is nothing but M bar cross B bar torque or couple, whatever it is here. The potential energy is minus M. I'm not teaching anything new till this point. It is as same as cut, copy, pasted concept of dipole, electric dipole. So now issue is if this magnet is in the influence of two magnetic fields. Two magnetic fields. One is B1, the other is B2. And the magnetic dipole aligns a specific direction, say, for example, theta with B2. and it's the equilibrium. Now, if you disturb, it will oscillate about that equilibrium position. Like for example, theta is some 30 degrees. Between 29 degrees to 31 degrees, it will oscillate about a vertical axis. Okay. So here, what law that will justify is the net torque is 0 here. So therefore, B1 MB sin theta torque, MB sin 90 minus theta is equal to B2 M sin theta. So therefore, M you cancel, B1 becomes B2 tan theta. This is called tangential law. Nothing new, we already know this. Right. If you have magnetic field like this and the dipole like this, and if this is theta, remember, drawn small angle theta, the restoring torque is given by minus mb sin theta because it is restoring. So this will provide I alpha given by minus mb theta for very small angle. So this executes SHM. So whose omega is given by root mb by I, and whose time period is given by 2 pi root I by mb. Two pi root I by mb. Any doubts till this point? Boys, you have any doubts till this point? Right. Next. The next aspect to discuss is already I have discussed. See, one important aspect I need to discuss is what are the different effects that when two magnets interreact. Actually, I don't know to what extent these things are considered to be a part of the syllabus, but still it's my responsibility that I need to discuss those things. Earlier, this chapter is considered to be huge because of different combinations. Now, fortunately, they have reduced, and finally, you got a very simple content under this chapter. Right. Now, dipole interreactions. We can assume three possible interreactions. Remember, I have just introduced what is force, what is couple or torque, what is potential energy, likewise. Before that, 1 minute, just before that, I just want to add some more points related to this. I see you already know in dipole, electric dipole, most of the cases we will take short bar magnets only. Electric dipole, we have already studied that at a point here, the magnetic induction field strength called B is given as B is equal to mu naught by 4 pi to capital M. Remember, distance always measured from center of the magnet. So 2m by dq. When I am writing this liberally, I am speaking about a short bar magnet. And this line is called axial line. Right. On the other hand, if you have the bar magnet like this, south and north, this line is called equatorial line. That line is called equatorial line. On it, like your dipole, I am not teaching anything new. See, try to please correlate whatever that I am discussing here equivalent to the dipole conditions of electrostatics. In dipole, you will find the field on the equatorial line like this, perpendicular to that. So let this be B axial and that is B equatorial. So therefore, B equatorial is mu naught by 4 pi capital M by d cube, where d stands for this distance. The axial equatorial line. Okay? So fields only important. Right. Now let us go for dipole-dipole interreaction. Dipole interreaction. Dipole-dipole interreaction. Now, first thing, relative positions. Next thing, force. Next thing, couple or torque. Next thing, potential energy. Which means, if you have two dipoles with their magnetic moment M1, M2, I am sure the same thing you have learned in electrostatics. Same, I'm just trying to bring the analogous part only. I'm not deriving a single thing in this because we already have that. So they were separated by distance r. See, if these dipoles are aligned in an order, they will experience an attractive force with each other. Now, that force is given by attractive force. I am writing only magnitude part. Mu naught by 4 pi 6 m1 m2 by r to the power of 4. Remember, it is the speciality of this 4. Power 4. Earlier, you know, inverse square law, inverse cube law. It is r to the power of 4th law. Okay? Next. Remember, in this case, there won't be any couple. 0. Why? Because M bar and B bar are in the same direction. But there is a potential energy. You know, already I've given minus M bar dot B bar. So it is U is equal to minus mu naught by 4 pi. I am not, what do you call, I'm not giving anything new. It's the same dipole of electrostatics concept I am copying here, literally. M1, M2 by R, ఇది వచ్చేసి R cube. If you have any doubt, you can check. I've given you fundamental relations. Right. This is the first part. The second part, of course, both are aligned in the same direction, but the only difference is they are parallel, of course, but both are coaxial and their equatorial line coincides in this case. Same distance. Remember, in axial condition, you will notice an attraction force. In equatorial condition, you will notice a repulsion force, even though both are directed in the same. Why? In axial case, field is in the direction of axial line. In equatorial case, field is opposite to the direction of axial. I mean, you can see here, It is opposite like this. Opposite to the direction of ember. So therefore, what was responsible for attractive force earlier, now it becomes a repulsive force because it is common equatorial line. Previously, it is common axial line. So therefore, now it is, earlier it is attractive. Now it is repulsive. Mu naught by 4 pi 3 m1 m2 by r to the power of 4. Even now there won't be any couple. Yes.
Direction. You do left arm right, downward direction.
So you didn't follow this in electrostatics. If, for example, due to M1, due to M2, for example, the field here is in this direction. Let this be B2. Due to M1, field at this point is in which direction? Always opposite to the dipole. That's all. So, torque is 0. Anti-parallel condition. Okay? Right. Right. What about potential energy? If there is attractive force, potential energy is negative. If there is a repulsive force, potential energy is positive. Mu naught by 4 pi m1 m2. Force off gada. Potential also the same. Now these two are very simple cases. The critical case is what I am going to give you right now. One is aligned like this. The other is aligned like this. M1, M2. Separated by a distance r. So depending upon the orientation, in this case, undoubtedly they will experience. See, this dipole will experience leftward dipole will experience a downward force, and the rightward dipole will experience an upward force. Fine. So depending upon the orientation, the force of magnitude is the same as the previous case, mu naught by 4 pi 3 m1 m2 by r power 4. What about potential energy? This system will not have any potential energy because always one with respect to other, m bar and b bar are mutually perpendicular to each other. M bar and B bar are mutually perpendicular to each other. So what will happen? Potential energy is 0. What about torque? Definitely there will be torque now. How? Let us see here. Let us see here. This is the magnetic moment vector. Due to this, field will be in this direction. And this is M bar. So this will experience a clockwise torque. Yes or no? Again, dipole, due to which field is like this. This is M bar. This will experience a clockwise torque. Similarly, this is the field and this is the magnetic field direction in this region. Due to this, this is the direction of the magnetic field in that direction. Remember, this is M1, this is B. So obviously, this will also experience a clockwise torque. But only difference is, in this case, the field is equatorial. In this case, the field is axial. They are different. 2:1 ratio. So therefore, on M1, in this case, on M1, the torque is mu naught, but MB basically. Mu naught by 4 pi 2 M1 M2 by R cube clockwise. On M2, torque is mu naught by 4 pi, half of this, M1 M2 by R cube clockwise. But potential energy is 0. చూసుకో నువ్వే. If you have any doubt, check. On M1 కదా నీకు కావాల్సింది. ఇది యాక్సియల్ లైన్. యాక్సియల్ లైన్ ఫీల్డ్ ఫార్ములా mu0/4 2m1 2m2 by కరెక్టేనా? Right. Because here the field is axial part. Here the field is equatorial part. So 2:1 ratio will come. Remember, I never ever seen a question on the basis of this. At least the last 2 years. You may ask me why you are teaching then. What if they question? What if they question? If we have an exposure of this particular thing, at least we will stay confident when to handle such questions across, right? So magnet based, these are the questions. Okay, there is an arrangement called vibration magnetometer, which was not there in NCERT, remember. In this case, the magnet, which is in the form of a magnetic needle, will align along the direction of the Earth's magnetic field, BH. Earth's magnetic field. And you will disturb that. It will perform oscillations. So the time period of oscillation is 2 pi root I by MBH. I refers to moment of inertia. Almost you can take it like a rod. You can take it like a rod. M L square by 12. And magnetic moment, you know. So some problems you can expect it on this. You will disturb that magnetic. It will oscillate in the plane. So accordingly, you will determine the time period. On the basis of the time period, they will question. But I don't see any questions on this for the last 2 years.
Cross B external అంటే exactly
ఇది
M cross MB MBH అన్నారు.
ఎక్కడ వేర్ టైం పీరియడ్ లో M into BH
అంటే
already that needle is at rest. Which direction needle is oriented? The needle will be oriented in the direction of the horizontal component of the Earth's magnetic. Wherever you are standing, you will face 2 components of the Earth's magnetic field. One horizontal component, 2 vertical component. So our needle responds to only horizontal component. That is the reason why all the compass box fail at poles. Earlier we used to have this concept in our syllabus, Earth's magnetic field. Now they are removed. Treating Earth as a magnet, Earth's magnetic field lines will be there. So when you have a magnetic field, there is a specific direction at a point where you have chosen. That point will have 2 components. One, a component at that place horizontal with respect to you. If you imagine the magnetic field vector in a vertical plane where you are standing, so it will have 2 components. One vertically up or vertically down, depends upon where you are standing. Southern or northern hemisphere. If once this syllabus is done, I will show you that, so that you will have an idea about what I am teaching about. Right.
magnetic ఇక్కడ magnetic
Bar magnet.
same magnetic
అంతే, pole strength into 12. Next. So I just introduced some concepts over here. See, before I start what you call the magnetic properties, magnetic materials. Magnetic material are studied in terms of two different factors: intensity of magnetization, magnetizing field. Now, let us first learn about intensity of. Listen to my words carefully. Don't get confused. We are using B till now for magnetic field, but that is not magnetic field. Technically speaking, when you are writing B as a term, Tesla units, you should mention it as magnetic flux density, magnetic induction field strength. Otherwise, never ever we used that. We will simply say magnetic field. But when I'm speaking about magnetic field, I need to be very careful. There are two terms related to that. That is the term which I'm discussing right now is intensity of magnetizing field. Remember, in fact, this is the one which is responsible. And this is the source. It is related to source. When you are sending current in a current carrying coil, in fact, this will establish first. Source. So therefore, it is defined as mu naught or that is the deal. That is the definition. So the ratio of magnetizing field to the ratio of to that of the magnetic permeability of a free space is what we will call as H. In fact, this is what we call as a source. Units for this one is ampere turn per meter or simply ampere per meter. This is related to source. Sir, when we have B, why there is a necessity to discuss about H? For example, when you are passing certain current in a solenoid, for example, that sets some n number of lines. Now you place a iron bar inside that. The iron bar gets magnetized and the total lines in that region is due to two reasons. One, due to the main current. Two, due to the magnetization of the material. So when you are speaking net, you are speaking about B. But the contribution of magnetization part of the iron, if ignored or if not considered, there is something field which is a source, which is primarily responsible for setting up the field. That is what we will call as intensity of magnetizing field. It is represented by letter H. Next. Intensity of magnetization. This is actually represented as I bar. Remember, if magnetizing field is the cause, the effect is magnetization. You place a magnetic material in a magnetizing field, it gets magnetized. So it is defined as dipole moment per unit volume. Dipole moment per unit volume. See, both have the same units. What is the units of intensity of magnetization? Again, it is ampere per meter, because dipole moment will have magnitude ampere meter square, whereas intensity of magnetization will have a units ampere meter square per meter cube. So it is ampere per meter. If you know one more important point, magnetic moment by volume. Magnetic moment is, suppose if there are n number of dipoles, if there are n dipoles, each of pole strength m, length 2l, volume refers to cross-sectional area into length, for example. Then literally, because aligning all n times 12 becomes capital L. So this one also you can use, right? And there is another term called magnetic susceptibility. I told you one point at the beginning of this: cause, effect. So we require some comparison to measure the relative things. Ante cause per unit effect. That term is called magnetic susceptibility. Magnetic susceptibility is represented by the symbol psi. It is defined as intensity of magnetization to that of intensity of magnetizing field. Because both are same units, it is dimensional less. Any doubts? That is why I don't teach all these things. Intensity of magnetization divided by intensity of magnetizing field is what we will call as susceptibility. Susceptibility is a scalar quantity. It has no units, it's a constant. Now, when I am classifying these things, definitely I need to express the magnetic properties in terms of these things only. And there is one more important point: magnetic permeability, like your dielectric constant term. Magnetic permeability. This is defined as mu, not mu naught. Mu naught means magnetic permeability of free space, vacuum. Now you are speaking about a material. So mu is defined as B by H. It is also, mu has dimensions, not a dimensional constant. It is not, it has dimensions. అది టెస్లా, ఇది ఆంపియర్ పర్ మీటర్. కాబట్టి దీనికి యూనిట్స్ వచ్చేసి హెన్రీ పర్ మీటర్. Because even dimension analysis also, they play key role, identification of units, right? Relative permeability. What is relative permeability? Mu r. It is defined as mu by mu naught. I am not convinced. Good. magnetic induction field strength in a medium divided by magnetic induction field strength in air or free space. This is mu h. This is mu naught h. Finally, this is mu by mu naught. Remember, it is once again a dimensionless quantity. ఇప్పుడు అదే చెప్పబోతున్నా. Right. See, let us try to understand a region inside a solenoid. Now remember, these are the lines, flux lines in air. When I am writing B, I am writing it as simply, that's all. That is the definition of B. Number of magnetic field lines per unit area. Now what happens in this region if I place a good magnetic material? Now inside this material, the lines are due to two reasons. One due to magnetization of the material, the other due to magnetizing field. You can see the total number of lines inside is due to two reasons, red color and blue color. Blue color corresponds to magnetizing field. Red color is due to magnetization of the material. So now tell me, if you say H alone, you won't get any picture. So now tell me, what is B inside? B inside is due to two reasons. Due to the air part, due to the magnetization part, which clearly implies B can be written as B naught is mu naught H, and this is mu naught I. Sorry, any doubt? Right. I.
డైపోల్ ఇండ్యూస్ చేసేది.
అవును దానివల్ల వచ్చే లైన్స్ ఐ ప్రపోర్షనల్ టు ఐ. ఇప్పుడు బి వచ్చేసి మ్యూ హెచ్, మ్యూ నాట్ హెచ్ ప్లస్ మ్యూ నాట్ ఐ. సో ఓవరాల్ వాట్ యూ కెన్ రైట్ నౌ, మ్యూ ఈస్ మ్యూ నాట్ ప్లస్ మ్యూ నాట్ ని కామన్ తీసేస్తే మ్యూ ఈస్ మ్యూ నాట్ టైమ్స్ 1 plus I by H. Anywhere you heard about I by H? Susceptibility. So mu relative is 1 plus susceptibility. So మొత్తం ఇప్పటిదాకా చెప్పిన దానిలో till now whatever I taught you, I require only this relation. For majority of the purposes, 90% of the questions from this chapter is on the basis of this equation. Now tell me, do you have any doubt till this point? చెప్తాను, ఇప్పుడు చెప్తాను రాబోయే 10 minutes. Now magnetic materials are basically classified into three categories. One, diamagnetic material. Problem is, if it is diamagnetism is a universal property. Diamagnetism is universal property. Even a ferromagnetic material will also have diamagnetism. But what dominates is the ferromagnetic property. Now the problem with these materials is, when placed in a magnetizing field, they will magnetize in opposite direction. In fact, they move from, generally magnetic material will move from weaker field regions to stronger field regions, whereas a diamagnetic material will move from stronger regions to weaker field region, which means if you see normal lines like this, magnetic field lines, say inside a solenoid, air as the material. Now you place a diamagnetic material inside, what will happen is the lines will go like this. They will go inside that. P inside is undoubtedly less than B naught. So this is the property of diamagnetic. You know, some lines will go okay, but still very less number of lines will pass through the material. In fact, if you take a superconducting material, a superconductor, you know what happens? Nothing will pass through that. దేనిలో ఏ ఉన్నదంటున్నా ఆపోజిట్ ఇప్పుడు కూడా B0. No single magnetic field line will pass through the material in superconducting. And B అంటేనే నెట్. B అంటే ఏమని చెప్పాను ఇందాక, tell me. Number of lines per unit area. ఏం లేదట్లా. Right. See, it is a universal property. It is universal property. So it is present in every material. Obviously, it is present in every material. Independent of temperature. No effect of temperature. Nothing. No effect of temperature. I'll give you some examples related to. Now, basically, you will find these materials, maximum such materials in diamagnetic materials, the spins of electrons are paired. Paired. Don't say unpaired. Paired. Paired గా ఉండటం చాలా మెటీరియల్స్ న్యాచురల్ ప్రాపర్టీ కదా. It is an universal property. Examples: bismuth, copper, silver, mercury, lead, water, hydrogen gas, and all inert gases. They are diamagnetic in nature. So how to identify the property called diamagnetic? Simple. They will have paired this thing, and it's a universal property. and no effect of temperature. And last but not the least, when you place a diamagnetic material in a magnetic field, magnetization do take place very weak, that too in